Okay, I hope you all enjoyed the break. We're back on the beginner-friendly spring track. I'm Cora Iverclad, your MC, and I'm thrilled to present the next topic, which is a fascinating topic, high-precision GPS positioning for spring developers, brought to you by Gunnar Hillert.
Hello, hello and welcome. Bienvenidos, hello from the middle of the Pacific to all the spring aficionados worldwide. My name is Gunnar Hillert, and I'm presenting to you the high precision GPS positioning for spring developers. So let me jump into these slides. And as I said, I'm Gunnar Hillert. You see a couple of pictures of mine that I grow in my garden. Otherwise, in my professional life, I'm an independent software developer, Java champion. I co-founded DevNexus, the professional developer conference many years ago. I'm an open source committer for previously for projects such as Spring Integration, Spring XD, Dataflow, and recently for the Java Marine API. Have been part of the Spring team for almost 9 years. And I'm also an avid plant collector, which brings me to the topic of high precision GPS. I have a large plant collection in my garden that I need to keep track of. And I learned over the past couple of years that plant labels don't work, memorizing doesn't work. And eventually, if you have hundreds of species of plants, that your collection, you need to keep track of what you have and even find it in your garden. So that is what brought me over to high precision GPS and what you can do with it. So in this presentation, I want to go and talk a little bit about some of the fundamentals around some of the terms you encounter in this field. So a little bit of theory. I talk about the hardware I'm using to make those measurements, of how to then get those measurements into my backend, into my applications, and how to process them, and then of course how to visualize those, and all this wrapped with 2 demos in this short brief period of time. And I hope that you get out not just anything around high precision GPS, but also some of the tooling around it that even might be useful if you're not specifically interested in the subject. Why high precision GPS? So in the past, you might have done, I think I have. In the past, you might have had requirements where you have like a Google. Oh, I'm sorry. I'm not screen sharing. I'm sorry about that one. Here we go. All right. So okay, back to the talk. I have my demos I'm showing as well, and so why high precision GPS? So on your Google Maps or OpenStreetMaps, you may have you may have placed markers, etc. But the accuracy, the zoom levels are not great, not high, good resolution of that. But also on your mobile devices, the precision of those GPS coordinates might be less than stellar. You might run into accuracies of like 8-9 meters, which for certain requirements are suboptimal, like in the areas of autonomous vehicles, robotics, precision farming, drone operations. You get into subjects like your surveyors are doing, right? Like infrastructure, keeping track of where your pipes are, your electric wiring, whatever it is, biodiversity, which touches on the needs that I do have in terms of keeping track of very fine-grained locations and of plant material. But let's maybe also reframe some of the terminologies. When we always talk about GPS, what we really mean these days is GNSS, which is a global navigation satellite system, since GPS is just one out of several systems. So GNSS refers to a constellation of satellites providing signals from space that transmits positioning and timing data to GNSS receivers, and then the receivers then use this data to determine location. And that's from the European Global Navigation Satellite Systems Agency. So we not only have GPS to deal with, but we also have GLONASS, Baidu, Galileo from the European Union, as well as various satellite-based augmentation systems like QGIS in Japan, EGNOS in the European Union. And your devices can take advantage of those to even provide further better accuracies. When I started out on this subject, the term that caught my eye was this dual frequency GNSS. There was a blog post by Sean Barbeau, dual frequency GNSS on Android devices, that had this promise, that you do have more than one frequency that your devices might use, and therefore provide higher accuracy, faster lock on onto the signal, and less, just increased accuracy on that. Interestingly, that support on devices that you can purchase in the US is still spotty in 2020. Whole bunch of the Chinese products do have that at this point. OnePlus which I'm using, does have that, but even Apple has not dual frequency support in its devices as far as I know. There is also like an open source Android app in the Google Play Store, GPS Test, where you can see that those abilities on, if you have those on your phone. So in my experience, and this is certainly not scientific, but so the quality is way better. You have a much better signal inside of buildings, which is good to know. But it's not amazing. You're not going down yet to an accuracy level of centimeters, just a few inches, which I like to have. And here's just a couple of screenshots from my data collection. So on the very left, I have a OnePlus several years old. I'm getting to an accuracy level there of maybe 9 meters. I do have, in this screenshot, I see GLONASS satellites as well as GPS satellites. Single frequency. In the middle, I have a OnePlus 8 Pro, which does have dual frequency GNSS, and you can see that in the in the listing of frequencies. So you see under the CF column, you have an L1, L5. On the very bottom, you have Galileo satellites from the European Union with E1, E5. So it does provide those satellites. I get down to, in this case, 3.8 meters. It seems to be a fairly way more reliable signal as far as I can tell. But as I said, not down to that extreme level yet. On the very right side, I do have the signal from my external GNSS receiver, u-blox, and this one is basically overrides the location services in Android. So the available information is more limited. However, the accuracy is portrayed here and you go down. In this case, it's 0.5 meters, but when you have the full lock onto the highest accuracy level, it will basically just show 0, which initially led me to believe the signal is bad, or the app doesn't detect it. But no, that is actually what happens here. So how can we do better, though? So in this regard, then we need to incorporate correction data, and that is key in order to get down to 1 to 2 centimeters of accuracy. So the key here is real-time kinematic positioning, RTK. And what that typically means in those setups is that you have what they call in this lingo rover and base station. Rover is basically your mobile device that is connected to an external GPS receiver and gets the data. It's get its positioning data. But then you still have a base station sitting in your garden or on your property or somewhere nearby, no more than 10 to 40 kilometers away, which basically gets correction data to your rover. So what often happens is you have a radio signal that is being emitted from the base station. Your rover gets the data, and that way they can eliminate any type of atmospherical or satellite errors they see, as they basically see the same sky as your mobile device, and can do some error correction there. There are a couple of other correction services that are beyond the scope, like PPP, RTK, and PPP. One thing you have to be aware when you operate in this space and the further you go in terms of accuracy, the harder it is to achieve that. So you have to understand this relative accuracy versus absolute accuracy. So, but what I mean by that is when you're in the field and you do measurements and you go down to a point, everything is absolutely perfect. However, if you maybe go with a different device, or your base station needs to, you basically reboot that if you don't know the exact position where your base station is, and it does basically a survey in mode, then you may have you get basically possibly a different absolute accuracy, which may deviate by centimeters, maybe even like up to half a meter. So it's tricky to get that really perfect down to the last centimeter. Another option is to for consuming correction data is NTRIP, which is RTK over the internet. This eliminates the need for a base station. So if you live, for example, in many mainland locations in the United States or in Europe, you have access to often public servers where you can actually subscribe to that data and get, and if you have those NTRIP stations close by, you can eliminate the need for a base station. There's basically what it means, basically the abbreviation network transport of RTCM via internet protocol. It itself uses an acronym inside, which is the Radio Technical Commission for Maritime. Only a German agency was able to come up with that type of complexity for an abbreviation, but so be it. With that, you can also manually process receiver data. So in the olden days, or people, it's certainly an option, is that you can take measurements in the field and then actually post-process the positioning data you have against those reference station. There's in the United States, there's a system of continuously operating reference stations, course, where you can download location data and post-process those, for example, with an open source library like RTKlib. You can then use that also against your base station. So I have not done it yet. So I get very good relative accuracy. In order to get to that ultimate level in absolute accuracy, I may need to fine-tune my base station location using post-processing. In terms of hardware, here's my setup, what I'm using. As I don't have access to any type of end-trip online correction data that transmits the correction data in real time, I have to use a base station and a rover. You see the base station on the left and the rover on the right. I'm using just a plain tripod where I'm mounting the antenna of my base station, and then I basically put together a couple of hardware pieces to wire everything up, a little casing, etc. And on my blog later on in the notes, I will post a link of all the pieces that I used to put everything together. So just in case, if you're interested in doing something similar, you will have all the pieces to make that happen. This setup is relatively low cost. If you look in some of the equipment that your professional surveyors are using, it is insanely expensive. But thanks to companies like uBlocks and ArduSimple, this type of technology became much more of a commodity, and you can use it in your Arduino project. So the boards I'm using, those are Arduino based, and it uses the uBlocks ZD-F9P module, which provides this very high accuracy GNSS support. And then you connect to your device via either Bluetooth or serial. In my setup, I have the ability to do both, which sometimes comes in handy, as you can connect different pieces of software to your devices simultaneously. And then I have there's a little radio antenna also on the rover and the base station that allows to basically get the correction data to your mobile device. So what do you do on so you have the hardware. How do you get it into your applications? In this regard, what works best for me is in Android, you have the ability to enable mock locations, which is an option under the developer options, and it basically overrides the location services. And therefore, once you have that and you have set up and you get the data into your Android device, you can then use them in any of your applications. It's basically visible as if it was the standard GPS or GNSS signal. I'm using a piece of software, open source, LeftBeer Encrypt client, which basically connects via Bluetooth to your external GNSS receiver and makes that data available in Android. And there are multiple applications in the Google Play Store. This, to me, was the most reliable. It has certainly not the nicest looking UI, but it was stable. And what is very important is it provides a good visual indication on the fixed type. So as you look at the various satellite constellations, you have different accuracy levels your device might get into. If you get into this fixed type RTK, that is the highest accuracy level, and that's when you see a lockdown all the way down to 1 or 2 centimeters, and your GPS coordinates literally almost don't move at all anymore. That's kind of like where you hit the excitement. What about iOS? That very limited support. You cannot override GPS there. You basically need a custom app integration, which there's very little of that. An option is, there's a blog post I'm linking in the slides, is on how to do that via Wi-Fi, how to get the messaging into your iOS device. But your target platform for taking measurements for the most part is Android, as that gives you the most flexibility. So once you get the position data into Android, you're good to go. However, what about processing the raw data that you do get from those external GNSS receivers? So the main standard in this field is NMEA 0183, which is by the National Marine Electronics Association. And it's used pretty much by all the devices. So everything is emitting this type of data. It is not specific to just location services. It's very heavily used for any type of equipment, particularly in the maritime space. Boating comes to mind. And it's a proprietary standard. So text-based is cool. That's nice. It's not as ugly to look at as binary protocols, which is kind of like the only alternative then when you go to interacting with external devices. But it is proprietary, so there's no cheap documentation, official documentation available. I think it's like $1,000 or $2,000 just to get that document, and you cannot even find it anywhere on the internet. So what's the best is probably uBlocks has some interface description that goes into the message level and provides really good details. There's a link in the slide for that. And there's some good Java support, and as well as open source support for processing those messages. So the message standard itself provides numerous what they call sentences. Those are message types. And if you look at the text output on the right side of the slide, you will see an orange. Those are basically the various message types that are collected for this particular output, like RMC, VTG, GSV, for example, is basically the satellites you have in view over your head. So there are multiple messages that give you, the position on the sky, signal strength, etc. And in blue, you have the identifier for the GNSS system. So you have GP for GPS, GL for Galileo, etc. At the very bottom, you will have also, there are vendor extensions that are also possible, so proprietary messages that might come in handy as they provide additional information. In this case, I have the uBlocks chip that I've been using is emitting several two messages that contain better information for certain scenarios, and those are then prefixed with a P. Processing those data is a little painful, and I linked a really hilarious article onto this by the author of the GPSD library, which is probably the preeminent Linux daemon for GPS devices and data, why GPSs suck and what to do about it. Quite hilarious, and when you start processing the data, you start hitting those pain points really early on. As I said, the alternative are proprietary binary formats. That's even uglier. And for processing those data points, the main library, as mentioned, is GPSD. That's also used on Android. It's a daemon for Unix-like systems, and it basically abstracts not just the data, but also it basically is aware of the hardware itself, because the underlying messages and the lack of defining what order messages come in, etc., requires a little bit hardware awareness, and it abstracts that all away and provides a JSON-based request response protocol. So if you need any type of real, probably production-ready exposure of the data points, that's probably the library to look into. We also have the Java Marine API, which I use for my demo purposes. Which has very good support for parsing the messages itself, but it has support for keeping track of message orders, but I'm not using it for that purpose. But it is a good library for parsing the messages itself and convert those into your domain objects. When you connect to external GPS receivers, as I mentioned, I'm using both Bluetooth and serial connectivity. So in the Java world, you have the best option is NR Java serial. that is under active development. It's a good, really good library to make those connections work. For my demo purpose, I have also looked into Blue Cove, which is the Java API for Bluetooth, JSR82. Really old, really tedious to get that to work cross-platform. I actually had to patch a jar file to make that work, as there's some native code involved. But it works. I have it in the demo. So if you have some more Bluetoothy requirements for your projects outside, for example, outside of GNSS, then this might be also something to look into. Don't look for any modern type of services like audio transmission of audio via Bluetooth in Java. That's simply not there. Also, a side note, if you may look into the space of connectivity, if you have non-serial USB requirements, also look at USB for Java. It's a JSR compliant library. The JSR is very, very old, but that's an option as well if you don't have serial requirements, serial connectivity requirements for your projects. So let's go into the first demo. So in this particular demo, I'm going to take raw NMEA satellite data and parse those and visualize those in my application. So I have a Spring Boot application here. I have the ability in that demo application to connect either via USB or Bluetooth. For my demo today, I'm using Bluetooth, but it's the demo, its application itself, which I will provide to you as well, will have both options. It does some introspections. It has the ability to query your environment and actually gives you a selection of devices you want to connect to. And then under the covers, I'm using Spring integration, which is an enterprise integration pattern implementation. It's a great book also that defined those patterns. And for this particular use case, it really worked really well. Since I have all kinds of different messages that require routing and need some massaging, and it just helps me for this particular demo to compartmentalize the various parsing logic and processing logic in my application. So I'm using Spring integration for this. On the right side, you have the various components of my Spring integration flow. And so I'm getting the NMEA data in. I will send them through message channels that are connecting the various components. Initially through a transformer, which is an NMEA to sentence transformer. So I'm basically taking the raw data, convert it into a more palatable domain object, and will then send it over to a header value router. So what I do here is to route the various message types that I'm looking at. And in this case, I'm looking at GSV, UBX, GSA, and GGA, which are basically, GSV is the satellites I'm seeing over my head. GSA is active satellites, provides also some accuracy information, positioning, etc. GGA for fixed data. So then route those messages to their specific service activators, which are basically just Spring services to store and process those data points. For the satellite and view GSV, I do have some additional requirements, as I do have this kind of weirdness going on that each message does not contain all satellites. So a message there contains only up to 4 satellite points. So if I have 12 satellites swirling over my head in the sky, I actually need 3 messages before I get all 12 satellites. So in this case, I'm doing a header enricher, which basically puts the some information from the message as to how many messages I'm expecting, how many there are, etc. And then I have an aggregator, which will basically combine, for example, those 3 messages into one, and then release those to my service activator, where I then can process that message. And all along, I'm using micrometer for visualization purposes. So, or for exposing the data, which I then can use that data to visualize. So I was a little lazy in this demo, and I didn't write a specific UI on my end, on my application. Just I have 2 REST endpoints that provide some data. But I figured I'd do for this type of setting, since I have dealing with message rates, message types, etc. I'm exposing this data using micrometer, which is an application metrics facade. It's kind of like, think of it like Hibernate for metrics. You can use that to various monitoring systems such as Prometheus, Humio, Wavefront, etc. And it's very simple to use within your Spring Boot apps. It is, however, not specific to Spring or Spring Boot. You can use it outside of Spring as well, but it makes it very easy within Spring Boot to expose those metrics, which then get consumed by Prometheus, a time series database monitoring system. And then ultimately it gets consumed by Grafana for monitoring and dashboarding. And that provides a really nice and smooth way to creating quickly UI dashboards. It's really kind of cool to get some really quick results going quickly. So let me jump into the demo itself. I jump into my Eclipse. I have my GNS NMEA demo. It is using. I have my my setup in Spring Boot. I have the ability to override the settings. I pre-configured my UPS, my Bluetooth GNSS receiver, which is already running here on the side of my machine. And then I'm exposing the metrics using Prometheus. And the cool thing is I can also just expose them equally to other monitoring systems as well, by just a flip of either an environment variable or from within my my YAML file. So when I start up the application, I should get, it will boot up the app, and I should immediately see that I get data into my application. So what I'm parsing out here is my horizontal accuracy estimate. So I do have already like a very high lock onto the satellites. So illustrated by that differential 3D solution status. And the estimate in terms of accuracy is down to 1.5 centimeters horizontally and 2 centimeters vertically. So that's basically what I have in my log files. My Spring integration flow. When it in Spring integration, you typically have the ability to not just do Java, but also traditionally XML for the visualization of your flows. I'm more old school there. I prefer the XML notation, but that's just me. And basically the same flow of the messages of the various Spring integration components configured in here. The various channels, the transformers, to convert the data, and then ultimately to process those. I'm referring to service activator on the very bottom here. So basically download that if you have a similar setup and look at the source code. It's pretty straightforward. If I do expose the various data points, that should. I have the connection types here that connects to the various devices, And then I'm basically just making those statistics available to Prometheus via Micrometer. I have a little bit of two very simple REST endpoints that are exposing my positioning data. I have one for satellites as well. The actuator that exposes the metrics, and then I can go either into Prometheus, which has some very simple visualization abilities. I can go into the graphs there, but the real beauty is in Grafana. So in here, you then have the I created a very quick dashboard of the various NMEA messages are floating through the system, GGA, GLL, etc. Get the accuracy estimates into my dashboard, the message rate, importantly the status of my receiver. So I'm in the differential RTK mode, as well as the number of satellites I'm going through the system. Really cool is also that Spring Integration itself provides by default integration with micrometer. So you have your some of the metrics that are coming from Spring Integration that were historically available via JMX. They are also exposed via micrometer and visualized here in Grafana. So that's the quick demo for this, but there's more. So if I go back into the slides, so I do have my hardware, I do have my my data, I get into my mobile devices, I have some way to process the data, but what do I typically do with that data, and how do I process those points and visualize those and work with the data itself that I'm collecting? And this is kind of like where you start dropping into the world of geographic information systems. Because what you need to do is, you run into those issues where you have a much higher need for much more detailed in terms of visualization. And you need a much more accurate base map. You need the data points, etc. So QGIS is like painting with GNSS coordinates. So you basically collect points. You can collect or record polygons, paths, and then basically use those data to visualize those in all kinds of different ways, connect them to all kinds of data backends from specific GIS flat files all the way to backend GIS databases such as PostGIS, which is a Postgres extension. It's an open source project and quite powerful. It's touching. Going to the details would be way beyond this talk. However, I did use this application to process my points and create like a very simple base map for my visualization points later on. So how this works is that I need to do field surveys, and instead of writing my own client application that basically where I have to create my own forms and maintain my own application, I can actually do that using QGIS itself. So there are various plugins available, QField and Input. I've been using Input, and what you can basically do is you create forms within QGIS and for specifying what type of data fields you want to collect in the field, which is certain what's the name of your plant, the certain checkboxes. It's little that you're designing like a little bit of an application. You can attach pictures to your data you're collecting in the field, and then that gets transferred into an Android or iOS device, and you can run your application basically on your device, collect the data, and then synchronize it back into QGIS. And once you have it in QGIS, you can then synchronize it into your backend systems, be it a database, or you can also export it into various flat files if need be, etc. I'm for my demo purposes, I've been using the CSV route. So I collected 2 data sets. One is for my base map, which basically is all my fence posts around my property or my garden area. So and then a second layer where I'm collecting here marked in orange the various plants I have in my garden. You can then also visualize the various data points in your map as well. For example, like I marked anything that is missing a plant label that is marked with a red dot, for example. So it's quite powerful. One quick advice there is that you need to take pictures with Open Camera, which is an open source application for Android. Don't use the internal camera, as on some of the camera models, they go up to, I don't know, 40 megapixels or so. The data volume is just prohibitive, and you should fine tune that, and Open Camera will give you that option. So that brings me to my second demo for this talk. And in this demo, what I'm doing here is I have my measurements, my application that my plans, my base map, etc., that I got into QGIS. I exported the base map as basically a static map, so it behaves very similar to your typical Google map or OpenStreetMap. You can zoom in, zoom out. It basically tiles those images. Use that as the base map, and then I'm using the plants I'm collecting or measuring where they are in my garden. Those are exported via as a CSV file. So of course I could have also possibly integrated that directly into my backend database, but for this demo purposes, this worked out quite nicely. And in its core, it's a Spring Boot application. It uses Spring data. It uses Hibernate GPA for the persistence of the domain model. I'm using the spatial extensions in Hibernate as well, which is a little bit of a mixed bag there. As you hit this as you hit the requirement sometimes between geometry and geography, so there's a little bit of a distinction there that for short distance it doesn't matter. For if you're measuring locations between big cities and on the globe, it matters really well and makes a huge difference. As a backend, I'm using Postgres. There are various other databases that store GIS information. You could use Mongo or MySQL has support as well. PostGIS as an extension to Postgres is certainly the probably has the most feature set, probably the most widely used one for that purpose of GIS. And then I'm using Leaflet for the visualization point of view. I'm using Angular as my main UI. Make it look a little nicer. I'm using VMware's Clarity design, which is a component library for Angular and beyond, developed by VMware, which is really nice if you want to have a quick UI, and it has already all kinds of enterprisey features like pagination, data grids, etc., built in. So if you're on the search for good visualization options in UI, particularly for enterprise application, that really works quite well. And then for the visualization of my map, I'm using Leaflet and the corresponding Angular library support for Leaflet. So basically, Leaflet, think of it as like Google Maps on steroids, almost, in a sense that you can customize anything and everything. So you have your base map layers. You can then put points on top of it, other geographic objects, etc. In this particular case, I'm using GeoJSON. which is a JSON format for geographic features. Get that via REST controllers exposed, and then have those overlay my map. So let's jump into the demo itself. Let me start that up. All right, I'm populating my data. So my demo is set up, and you can when you check that out, it will take the CSV file, populate the database, get that all running, and then when I go into the demo for my plans, I have a REST API of a paginated list of plans using Spring Data. And then I can go into the details of the plans itself. And I'm also exposing not just the plant itself, but also what plants are nearby for that particular plant. So so that's a feature of when you're dealing with geographic data, is that you constantly would like to know what is within a certain range of my application within my certain objects, and you can query for all that information. In the UI, I have my URI running here, should retrieve the data. I have my Clarity VM UI here, where I have a list of the various plans I do have in the application. I have a little bit of customization, like a highlight in orange all the plants that do miss a plant label. So I need to go out there and put something into the ground. And then when I go into the details, I can then, I'm exposing my genus and species, a number of plants that are nearby. I expose a picture that I'm storing in the database as well. Your requirements, of course, may vary in that regard. And then I can go into my garden. So here I do have my map. I don't have anything highlighted right now, but let me expose the layers. I have my custom garden area that I do have. So I have a little bridge over here, little table, my little fenced in areas that I'm visualizing as my garden. And this is for demo purpose, but you can go really fancy in terms of like what you visualize. You can geo-reference images and create really nice work products there. And then on top of that, I have my plants. So I have all my markers that I do have. When I click on it, I basically show you what type of plant that is. And those are the individual markers. So this is a GeoJSON file that I'm exposing from my Spring app. And then from here, I also have a clustered view of the plants itself. So often, like, it's getting too convoluted, you rather want to have, as you zoom in, provide a way better detail of your markers. And it also shows you like the area in which those plant markers are. When you click on them, it provides you a detailed list of where those are. So that's pretty much the extent of this application. So in terms of the backend, it's literally quite simple. I'm storing my images. I do have that's the old application, but basically I have a couple of just have a plant and image that I'm exposing. I have an importer here that imports the CSV data. If you have more complex environments, you can probably use something like Spring Batch to have a much more powerful import experience. And then in my plant controller, I'm exposing my plans, my GeoJSON object, where I'm basically creating a feature collection, which is part of GeoJSON support in Java, and I can create those features into my feature collection, expose that as a JSON file automatically. And then when I get my plans here, and I do retrieve my plans itself, and then I query also like in which get plans within radius. So this is a Spring Data query here, where I'm basically select the plant, and then here it's a PostGIS function that I'm calling with the radius. And that's pretty much what there is for this particular demo. I think I'm slowly running out of time here, but please ping me if you have any questions, if you like dig deeper. As part of this whole homeschooling experience, I was a little bit behind in finishing up my demo, so please give me a few more days for finishing those up. I'm providing in the instructions for each of those demos. I'm also providing Docker. They're running Docker containers, so if you want to set up a quick PostGIS database, it will use Docker Compose to spin that up. The Grafana and Prometheus as well, to have a quick startup experience to get those demos running quickly. I just need to do a little bit more polishing on those on my end to make those available. If you have any questions, follow me on Twitter, ping me on LinkedIn. I will also make the information on the hardware pieces available on my blog, hilart.com. And yeah, the source code will be on GitHub. It's not up to date yet, so we'll do that next day or two. So please stand by there. And otherwise, thank you so much for joining me for this particular talk. If you have reach out to me. I hope you got something out of this talk. And if it's not just for specific GNSS needs, but for just getting certain demo data. If you like Grafana, I hope this gives you some good pointers of how to dig deeper. And throughout the entire slide deck, I made sure that I have a few links to the various projects there as well. So so you can use that slide deck as a good starting point. So with that, thank you so much for this presentation. And I think there's a channel where you can have additional questions, and I will be there shortly.
Wow, excellent presentation, Gunnar. Thank you so much for that. Remember, you can continue the conversation on the Slack channel specific to that session. There's also going to be a link to Q&A that will be held for the next 15 minutes or more or less with Gunnar. So that link will be in the Beginner Spring Friendly channel on Slack as well. And other than that, take a break, stretch your legs, get a glass of water, and we'll see you back in about 5 minutes for the next presentation.